Hello, my name is Robert Smith and I'm with New River Community College, and today we are looking at the relationship between the equilibrium constant and our Gibbs free energy. And we can form this relation through the equation delta G at standard state is going to equal negative RT natural log of K. Okay, so in order to get K, we need R, T, and delta G. Well, R is our gas constant. R is equal to 8.314 joules per mole Kelvin. And T at standard temperature and pressure, T is going to equal to 98 K. So now we just need delta G in order to find K. So delta G from our previous videos, we know that our delta G is going to equal the delta G of the products times their coefficient minus the sum of the delta G of the reactants times their coefficients. So it's going to be 2 times the delta G of HI, hydrogen iodide, which is 1.30 kilojoules per mole, minus the delta G of H2, which is just a 0 because it's a standard state. And you might be tempted to do that also for I2. However, I2 is not in standard state when it's in its gaseous form. It does have a Gibbs free energy associated with it for its formation. So, and that Gibbs free energy is 19.37 kilojoules per mole. So our delta G is calculated as negative 16.77 kilojoules per mole. And then we just need to rearrange this equation here in order to solve for our K value. So we'll start by dividing both sides by negative RT. So now we have natural log of K is equal to negative delta G over RT. And then if we raise everything to, we make everything the exponent of e to that power, we end up with K is equal to e to the negative delta G over RT. And then it's just a plug and chug. And if you do that, you get negative times a negative, so a positive 16.77 times 10 to the third joules per mole. Again, we're dealing with joules per mole. You can just as easily switch the R constant to be kilojoules per mole Kelvin, but I just chose to do the delta G in terms of joules per mole. Just make sure your units are consistent so that they cancel out properly, because the unit over here should be, there should not be a unit associated with that term, just as there's not a unit associated with K. So we have joules per mole, and then 8.314 joules per mole Kelvin. So our joules and moles have canceled, and then times 298 K. So the kelvins cancel, and we're left with 16.77 times 10 to the third divided by 8.314 times 298 K, or just 298 rather. So that gives you a K value of 870.2. And that's how you would solve using this equation here.